Okay, so yeah, it's recording. This is a graphing rational functions problem. Um, and it was the lesson that was done Thursday, I think it was October 17th. Let me see. Yeah, October 17th. So if you're absent, this would make a good video to watch. And in the problem, I give you this nasty looking rational function, and you're supposed to end up graphing it by analyzing all these different things about it. And I give you a hint to get started. One of the zeros for the numerator is x equals -5. And the reason that's useful is it often helps to factor these as much as you can. So if I just take the numerator and try to factor it, 2, 8, -22, -60, I know that -5 is one of my factors. So if I do this quickly here, here's 2, -10, -2, 10, -12, 60, and the remainder is 0, which is good because it was supposed to factor evenly. So what I know now is I can write the numerator as x minus -5, so x plus 5, and then 2x squared minus 2x minus 12. And then I could even factor this more. That's going to be x plus 5, and then a 2, and then x squared minus x minus 6. And then if I put the 2 in front here, I can factor this even more and get x minus 3, x plus 2. So this is just the numerator here. The denominator also factors. So if I just go straight to this, f of x equals. So numerator is the same thing that we just wrote. And the denominator, if you factor that, turns into x minus 4, x plus 2. So this is the factored form. We also have the original form up here. Depending on what we're looking for, they're both useful. One thing that I want to note right here, the domain is x cannot be 4 or -2 because that puts a 0 in the denominator. So we'll just kind of remember that. Another thing is that this function is, it looks just like g of x. I'm creating a new function here where I've canceled the x plus 2's. So it's 2, x plus 5, x minus 3 over x minus 4. It looks just like f, except that the holes are filled in, right? The hole that would come from the -2, x equals -2. So when I filled in the hole, that term for this function that looks just like it except the holes are filled in, so let me write except holes filled in. This type of function where you cancel out those terms, that's called the extended function of f. Okay, so we'll just kind of keep this on the side for now. Okay, so let's find the intercepts. All right, so x-intercepts. Well, that you get by setting y equal to 0. So set y equal to 0. And if I set y equal to 0, then that's saying 0 equals that whole fraction, right, which is 2x plus 5, x minus 3, x plus 2, all over whatever's in the denominator. But the next step I'm going to do is multiply the denominator over to the other side. So it's really the same thing as just saying what I have right there. The numerator has to be 0. So if I divide both sides by 2, I can just get rid of the 2 here. 0 over 2 is still 0. And then I know my zeros are going to be when x is -5, when x is 3, or when x is -2, which is almost right, except this one doesn't count because it's not my domain in the first place. So my zeros are really going to be -5, 0, and 3, 0. So there are my x-intercepts. Okay, the y-intercepts. So that would be set x equal to 0. Okay, and you could set x equal to 0 in this factored form here, but I think it's actually easier to go back to the original and set x equal to 0 up here because this disappears, that disappears, that disappears, that disappears, that disappears, and you're left with negative 60 over negative 8. So if x is 0, y equals negative 60 over negative 8, which turns out to be 7.5. So I know that I have a y-intercept at 0, 7.5. Okay, some other relatively simple stuff. We know that we have a removable discontinuity at, so I'll write this over here, removable discontinuity at x equals negative 2 because those cancel. And the way to get the y value for it is we can plug it into the function that looks just like it. So g of negative 2 turns out to be 2 times negative 2 plus 5, negative 2 minus 3, all over negative 2 minus 4. So that ends up being, if you work it all the way out, you get 5. So there's a hole at negative 2, 5. And then, so that's if we cancel the x plus 2's. The one that doesn't cancel, that's where we get our vertical asymptote. So vertical asymptote, x equals 4. And then the thing we have left to do is the end behavior asymptote. So, end behavior asymptote. Okay, and remember the end behavior asymptote, any rational function you get, you can always write it as q of x, the quotient plus the remainder over the divisor. And remember that the remainder always has a degree less than the divisor. And so if you end up looking at what happens when x gets really, really big, this thing always turns into 0 as x gets to positive or negative infinity, which only leaves you with the quotient. So the quotient is always the end behavior asymptote. So for our problem, we're going to do long division on it. So the numerator was 2x cubed plus 8x squared minus 22x minus 60. And the denominator was x squared minus 2x minus 8. Excuse me. And so if I figure out what my first term is, it needs to be 2x, so that when I multiply, I get 2x cubed here. And then 2x times negative 2x is minus 4x squared, and then minus 16x. And so now if I subtract, I'll get 8 minus negative 4, so 12x squared, negative 22 plus 16x, so minus 6x. Now I can bring down the negative 60. And if I add in the, let's see, if I add 12 here, then I'll get the 12x squared that I want to get rid of, minus 24x minus 96. And if we subtract this out, let's see, we get 18x plus 36. So that's the remainder part. So it would really be 18x plus 36 over the divisor. And remember, the remainder over the divisor, if I'm looking only as x gets really big or really negative, this becomes 0. So my end behavior asymptote is just the quotient part, not the remainder over the divisor, and that's y equals 2x plus 12. Okay. Since it's 2x plus 12, that's like mx plus b, it's not horizontal, it's a slant asymptote or an oblique asymptote, whichever term you prefer. Okay. All right, so we got a whole bunch of information now in these red boxes and in this red blob here. So now at this point we can do a sign chart. Yeah, at this point, after all that. So the sign chart, normally we always put the x-intercepts on there because that's where the graph could change from positive to negative. So negative 5 and 3 have to go on my sign chart. Negative 5 for my x, 3 for my x, and the f values are 0 and 0 there. But other places that you could change would be at a vertical asymptote, like 4 here. Because it's possible, and I'm not saying that the graph has to look like this, but it might go down here and then switch signs to above the axis there. So negative here, positive there. So if that's the case, then I need to check that. So I'm going to put 4, x equals 4, but it wasn't a 0, it was the vertical asymptote. Now this is sort of a moot point, but the removable discontinuity, if the y value had been 0 there, then you would have gotten a hole right on the x-axis. So it's possible that you could change signs there from negative to positive as well. Since it's already positive 5, it's not going to matter, but I'd say it's good practice to check it anyway. So I'm going to put, let's see, it's at x equals negative 2. So negative 2, removable discontinuity. So you can plug in a bunch of points into, probably you want to use your factored form here. So I'm just going to copy this and paste it back down here. Okay, so there it is. And if you plug in points, I'm just going to give you the sign chart. So it's negative here, stays positive, negative, and positive. Okay, so at this point we can graph the thing. So here's my y-axis. Here's my x-axis. Let's see, I've got a 0 at x equals 3. I've got a removable discontinuity at negative 2, 3, 4, 5, 6. So right here, I have to be at a 0, negative 5, 0. I have to have a 0 at 3. Let's go by 2's on the y-axis. So this is 1, 2. I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So 2, 4. I know that my y-intercept was 7.5, so that would be about here. I had a removable discontinuity at negative 2, 5, so that would be a hole right here. And I had a vertical asymptote at x equals 4. Actually, let me do the asymptotes in a different color. So here's x equals 4. And then I have that end behavior asymptote, that slant asymptote of 2x plus 12 right here. So 2x plus 12, I'm going to start 2, 4, 6, 8, 10, 12. And then it's a slope of 2. So it's up 2 over 1, up 2 over 1. If you figured out, okay, what happens when y is 0, remember that slant asymptote is 2x plus 12. So if y is 0, then x ends up being negative 6. So then I know that it'll cut through there too. So if I draw in this asymptote, looks like this. And then let me extend this one a little bit more. Let me do this. I'm going to move that up a bit. Okay. All right, so there's my picture. So we need to actually graph the thing. So notice here, it starts out negative. So I'm going to start out negative, and I want it to look like my end behavior asymptote. The slant asymptote doesn't tell you much about the middle of the graph, but it does tell you way out at the ends, it better look like this and this. So at least I've got that. And then I know I've got to go through here. It follows the sign chart because I was negative, and then I was 0 at negative 5. Then I got to go positive till I get to my removable, so it's above the axis. Then it stays positive after the removable until I get to the y-intercept, and it stays positive all the way till I get back to that 0. So it stays above the axis right up until I get to 3. And then notice it goes negative after 3. So it's got to go negative, and at some point you hit this asymptote, so the asymptote forces you to go to negative infinity. And then right after 4, I'm positive. And since there's a vertical asymptote at 4, I'm going to have to start at positive infinity. And then I don't know if it actually crosses this slant asymptote or not, but you can kind of, you know that it's got to look like the asymptote afterwards. So based on what we've learned so far, you can't determine if it crosses or not, but you can guess that it kind of looks like that sort of, this sort of shape right there, kind of a slanted V. So the red part is the actual graph, and it meets all the criteria that we figured out. Okay, kind of a long problem, but I hope that made sense. All right.